You first go along the longest bridge to the next one, to the next one, to the next one. So for this molecule here, I can say, let's say I'm going to start numbering here. I'll call this number 1. Then this would be a 1, 2, 3, 4, 5, 6, a 1,6-dibromo. Okay. Then we name the bicyclic part. And so how many carbons are there total? 6, 7, 8, 9. There's 9, so it's a no name. And then in terms of the connectivity of the bicycle, the connectivity here is going to be a 1, 2, 3, 4 stepping stones on that bridge, 1, 2, 3 stepping stones on that bridge, and 0 stepping stones on the middle bridge. What do I mean by that? Well, I'll show you that in the next slide. But so this is going to be called a bicycle 430, no name. Total number of carbons is what you want in your parent name here, and then ANE for the suffix because it's going to be an alkane. Okay. Now, if we look at oh, and one more thing we have to specify here. So we did say it's a 1,6-dibromo, but we did not specify whether or not the bromines were cis or trans to each other. In this case, they're trans. So if you don't specify trans in the very beginning of the name, then maybe what we're trying to imagine is a molecule where both bromines are coming out of the paper, or maybe both bromines are going into the paper. So here we're going to have to specify trans at the very beginning of the name to get the full, correct, unambiguous name for this compound. So if we look at another example here, a couple of examples. So here's where we have a bicyclic compound. This looks a little more complicated because what we've done is instead of, let's just break this bond right here, okay? And if we break this bond here and move it over here and attach it here, then it looks almost exactly like the compound we're just looking at on the previous page, right? And so that would be having a 0 for the last number inside the brackets. So what would the numbering be for this one? Well, this one has on a stepping stone. Think about stepping stones, right? So we're going to meander around the bridge. We've got 1, 2, 3 stones here. We have 1, 2 stones here. And we have 1 stone there. So from the bridge heads, where I like to think about where like the rope bridge is being anchored, we have how many ways of going around the rope bridge, or how many different rope bridges are there? They're moving through space. Well, you have one that's got 1, 2, 3 steps, one that has 2 steps, and one that's 1. So this one you would call a 3-2-1 bicycle, right? So the total number of carbons is going to be 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be an octane. So it's going to be a bicyclooctane, but because there's a number of ways you can draw the bicyclooctane, you can actually connect, the carbon 7 you can connect to here, you can connect to carbon 2, you can connect to carbon 8, right? There's a lot of ways of drawing this bicycle, so you have to specify it. This one in particular is going to be a bicyclo 3-2-1 octane. Now, in terms of the numbering, here's where you have to be careful, because you can't say, okay, well, the chlorine is the higher than an alkane here, and so I want to make sure that that's going to be number 1. Well, you can't do that, because if you make chlorine a lower number than 8, you're actually going to be numbering the wrong part of the bridge. You have to go the longest stepping stones first, then the next shortest, then the next shortest, and so on. So here you have no choice. We're going to say I'm going to start at carbon 1 here, or carbon 5, doesn't matter. And I'm going to go around the bridge. I'm going to say I'm going to do 1, 2, 3, 4, 5. Then I do the next bridge, which is 2 stepping stones, 6, 7. Now I've already numbered this once, so I'm going to have to skip it. You don't want to double number that carbon right here with both 1 and 8, okay? So once we get to here, 5, 6, 7, skip this one, and then 8. So that means the chlorine is on the number 8 carbon. So that's why you call it 8-chloro bicyclo 3-2-1 octane. And if you look at the example on the right-hand side here, so here we've got a compound that has a total of 9 carbons, right? It's like the one on the slide we saw, the first slide. And we have, total of 8 carbons. And so when you go to do your numbering, you want to pick a bridgehead. And so I'm going to pick number 1 here. I'm going to go the longest bridge first. So 1, 2, 3, 4, 5, 6. Then the next shortest bridge, 7, 8, 9. And then the last bridge is not there, so it's going to be 0. So that's going to be a 1, 2, 3, 4, 3, 0. So it's a 430 no name. It's a bicyclo 430 no name. Now there's one substituent on this thing, and that one substituent is right here. That's a methyl. So way at the beginning we say 8-methyl bicyclo 430 no name for that one. Okay. If we look at this one down here, that carbon there, that's a bad example. Let's not do that example there, because I can't read what that actually is. And of course, my structures are always done in ChemDraw, and so they're nice and clean and easy to read on exams. So you don't have to worry about this kind of an issue on an exam. But so just here's the basics to remember for bicyclic nomenclature. You're going to pick one of the bridgehead carbons. You're going to start going around the stepping stones of the rope bridges. You're going to do the longest bridge first, then the next shortest, then the next shortest. And then you're going to use the nomenclature of bicyclo brackets blah 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 alkane. So it's going to be bicyclo. What goes in the brackets is going to be the number of stepping stones on the bridge. So you don't count the anchor points. You don't count the bridge heads. And then you have your bicyclo. In case here, bicyclo 321 heptane, bicyclo 321 octane, bicyclo 430 no name. That's how you number it. Always start at the bridge head. That's going to be kind of confusing in a second, because we're going to go over the nomenclature of spiro compounds. And for spiral compounds, if you see how this one's done, it says, okay, so, by the way, a spiral compound is one where you have 4 carbons, or 4 pieces of cabbage or R groups bonded to one central carbon. So it kind of looks like an infinity sign in the middle there if you put your fingers together, where we have this here is called the spiral carbon. Okay, and so the definition of how you name these says you take the infix spiro followed by square brackets, just like we were doing with the bicyclo, but now it's going to be spiro brackets instead of bicyclo brackets. And then inside the brackets, we can have the number of atoms in the smaller ring, then the number of atoms in the larger ring, and separate each by a period. So in other words, we're actually doing a couple things backwards here. Number one, instead of going 4, 3, 0, in this case we'd be going 0, 3, 4. We're gonna go from smallest to largest. That's number one. That's an issue. But number two, when you start numbering your spiral compound, where do you start numbering? You never start numbering on let's call this the bridgehead carbon, but it's the spiral carbon. Why do we start numbering there? Because UPAC decided to say that, well, in this case, we're going to start numbering on the carbon adjacent to the spiral carbon. Now, that's, to me, I think, like if I had been a part of UPAC at the time, I think I might have said, well, you know what? If we make it such that we do the numbering the same-ish for spiral compounds and for bicyclos, it'll make it easier to remember that rule. However, they chose to go with this route where they're going to say, for bicyclos, you start numbering on the bridgehead carbon, and for spiros, you start numbering on the carbon next to the spiral carbon. Is there a way that's an easy way to remember that? Here's the way I remember it. Isn't it true that if I go back and look at a bicycle compound, okay, this bridgehead carbon here, can I put a substituent there? Yes, right, because I have a bromine. This is how I got the 2 dibromos on the bridgehead carbons. So you can put a functional group on a bridgehead carbon of a bicyclic compound. So therefore, you want to start numbering at the bridgehead carbon. Now, if you look at the spiral carbon, is it possible to put a substituent on the spiral carbon? No, not ever. It's already got its octet full. You cannot put anything, you can't put a bromine here, otherwise you broke the octet rule. So I think maybe the easy way to remember that for spiro nomenclature, you start numbering on the carbon adjacent to the spiral carbon instead of the carbon itself. The way to remember it is that you can't ever put a substituent, a halogen, a methyl group, whatever, you can't ever put that on the spiral carbon, but you can do that with the equivalent of the bicyclic, which is going to be the bridgehead carbon. Okay? Then you just have to remember that it's going to be the reverse, whereas with the bicyclic stuff, we go from larger to smaller, and for the spiro stuff, we go from smaller to larger to larger. Okay? So, as an example, let's take a look at this and see if we can name a compound with this nomenclature. Okay, so I have 2 spiral compounds here on the screen. A and B, and they both have the same number of carbons in the parent chain. They're both decanes, right? So we have 6, 7, 8, 9, 10 carbons in this one. We have 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons in this one. So they're both decanes, but they're both spirodecanes. Whoops. They're both decanes, but they're both spirodecanes. Okay. And actually, now that we see that there's an alcohol on there and a chlorine and a bromine, we have some functional groups you have to deal with. And so between the chlorine, the bromine, and the alcohol wins the highest priority. So these are not spirodecanes, they're spirodecanols with an OL suffix, right? Let's go through the numbering of this. Remember, for the numbering, we go from now from larger down, we're going to go from small up, okay? So if we look at A, I have my spiral compound here, spiral carbon here, and I could start going around the ring this way, or I could start going around the ring this way. I am not going to go around the ring into the 6-member ring, right? I'm going to go to the smaller ring first. So what do I want to do here? Do I want to call this a 1 bromo, 3 chloro? Because I think I also could call it a 1, 2, 3 chloro, 4, 5 bromo, right? And when you see that, you can say, okay, so this makes sense that I want to use the smaller numbers, and so I'm going to call this, I'm going to go around this direction here. I'm going to call this a 1 bromo, 2, 3 chloro, then 4, 5, 6, 7, 8, 9, 10. So again, 1, 2, 3, 4, 5, 6, 7. So that's why the alcohol is in the number 7 position. That's going to be a heptane, or this would be a decane 7 all, or a 7 decanol, right? And so once we have everything sort of numbered and laid out, we say we have the 1 bromo, we have the 3 chloro, we have the fact that this is a spiro compound. The spiro has 2 bridges that are going to be a 4, 1, 2, 3, 4, 5 for the spiro. There's 10 carbons total, so it's a decane. It's got an alcohol on carbon number 7, so it's a 7 decanol. And you put all that together in a sentence, and we end up with this right here: 1 bromo, 3 chloro, spiro 4, 5, decane 7 all, or I prefer to put like 7 decanol on that. Okay. Now you take that another 10 carbon compound that's a spiro compound, like the one over here, B, and you say, well, okay, so what's different? Well, the difference is going to be the numbering, and also in terms of the number of stepping stones on the bridge, so it goes in the bracket, is not going to be 4 or 5, like the molecule A on the left. What's going to go in the bracket is going to have 1, 2, 3, 4, 5, 6 carbons on the larger bridge, 3 carbons on the smaller bridge, and so we go from smaller to larger. We're going to call this a spiro 3-7, or 3-6. 1, 2, 3, 4, 5. Spiro 3-6. Okay. So then we're here at the spiro carbon, and we're going to say, okay, so we're going to start numbering by going to this way, to the clockwise, or we're going to start numbering counterclockwise. Now, when you look at it, this is a little bit tricky because you could say, if I go clockwise, I'm going to call this a 1 bromo, 3 chloro. If I go counterclockwise, I'm going to call it a 1 chloro, 3 bromo. And there, the numbers are the same. It's not like I'm coming up with like big numbers for the one direction and small numbers for the other direction, where I would say that would be my guiding post. It's my guiding principle there. Here, it's going to be a 1-3 and a 1-3 no matter how I cut it, right? So you have to say to yourself, well, then, I don't know, what kind of a rule would you do this, or how would you logically go about doing this? And remember, when we were looking at the UPAC rules, one of the things that was in there was that whole thing about alphabetizing, which I'm not really, that picky about. But if you're taking a standardized exam and the question is, which of these 4 choices is the correct name, and one of them is correct and it's UPAC, and one of them is correct and it's got the numbering backwards and it's not alphabetized, you better go with the UPAC because that one is going to be more correct. The other one is only correct in as it is going to be unambiguous, and that might be fine for if you're in my class, but if it's asking for the best answer is going to be the UPAC type answer. So is there going to be a preference for going clockwise or counterclockwise around the 3 carbon ring here? Yes. Why? Because when you go to the alphabetization part of this, you're going to want to put the bromine before the chlorine. And if you know you're going to want to put the bromine before the chlorine, then you can call it a 1 bromo, 3 chloro. Okay? So we have a 1 bromo, 3 chloro, and then we have a 3, 6, so it's a spiro decane. Spiro decanol, it's going to be a spiro 3-6, decane 7 all, or, so remember it's going to be 1, 2, 3, 4, 5, 6, 7, 8, or it's going to be 1, 2, 3, 4, 5, 6, 7. I'm going to go with the 7, okay? And so I'd actually put the 7 here, so it's going to be a 7 decanol, but decane 7 all doesn't really matter. Is the correct answer either way. Okay, the 2 that I saw on the previous slide that yes, these are just some more bicyclos. We'll just run through real quick. So here's another dibromo. It's a bicyclo. It's going to be a 4-3-0 bicyclo, and we have 2 bromines. So the bromines are going to be on carbons 1, 2, 3, 4, 5, 6. So 1,6 dibromo, and a 1,6 dibromo bicyclo 4-3-0, no name because there's 9 carbons total. And then at the very, very front of the name, we have to specify the relative configuration of these bromines to each other. And the relative configuration is they're cis. They're both coming out of the paper. Okay. So if you leave that cis out of there, then we could be looking at the one we did on the first one, on this one, which is going to be, could be trans. So you have to specify that it's 6. Cis, not 6, cis. This part of the name down here, I'm going to say don't worry about right now because really, if you look at it, where's Waldo? Identical, 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 identical. What's going on here? So here we say, I'm going to call this one a cis 1,6 dibromo. And here we're saying it's a 1s6r dibromo. Well, those are the exact same thing, but you need to understand what R and S stand for, and that's actually the chapter coming up after this on stereochemistry. And once we get through that chapter, then actually we will no longer use cis or trans. We'll always use R and S when we're going to give our absolute descriptors of these configurations on these atoms for these molecules, for naming them. So there's your full name. Cis 1,6 dibromo, bicyclo 4-3-0, no name. And then here we've got a bicyclo, but it's going to have 2, 2, and a 1. So it's a bicyclo 2-2-1, right? Here's your bridge. There's carbon number 1. You start walking around the bridge, you encounter 2 stepping stones, you encounter another 2 stepping stones. Don't double count this carbon, so just go up here over the top, and that's going to be your 7th carbon. So it's a 2-2-1 heptane, or a bicyclo 2-2-1 heptane. But then again, it's not really a heptane A and E because we've got this alkene here, right? So it's going to be a alkene. So you want to specify where the alkene is, and it doesn't really matter whether you start numbering from here. It's going to be called a 1, 2. So it's going to be called a 2-ene. But even if you start numbering over here, it's going to be a 1, 2-ene. You would not want to say, well, wait a minute, but this is a 2-carbon bridge. That's a 2-carbon bridge. Why don't I go for my walk around this side first? And then I'll call this a 1, 2, 3, 4, 5-ene. Well, why would you want to do that? If you go around the bridge that has higher priority with the suffix with being E and E, then you're going to give the lower numbers. That's the way you want to do that. Okay. Bicyclo 221 heptene or heptene, 2-heptene or heptene 2-ene. That's actually very similar in structure to a molecule I think you'll be using in the lab when you do the lab part of this course, where it's a bicyclic compound. It actually has also got 2 methyls here, so it's got that's 3 methyls total. It's going to have 1 methyl here, and it has 2 methyls here on the bridgehead carbon or in the way at the top, and then it's got like a ketone on this carbon here, and that's the ketone that you're going to do your chemistry on when you learn how to do chemistry of ketones. So you'll go back and practice your bicyclic nomenclature on something you're actually making in lab when you get to that. Okay, so last thing I want to talk about then is just we want to look at conformational analysis of these alkanes, and conformational analysis basically means another way to think about that is interchange or swap out the word conformation or conformational with the word rotation. Just like remember when we were looking at the types of isomers, and we said one type of isomer is a conformational isomer, and I said that's also oftentimes referred to as a rotamer or a rotational isomer, because really what you're doing there is just rotating around a single bond. And I sometimes have a hard time, including that as an isomer, because to me, isomers mean you change the functional group, you change the position of a functional group to a different position, you change something like, real about the molecule. With conformational isomers, what you're looking at is, it's like saying you have these compounds that can rotate around one of the bonds. And when it rotates, that's going to make it turn into a different isomer. And it's like, really? Because, you can't give a compound a name, a new name, every time it does a little bit of a twist or a little bit of a turn. Now, if it makes a bond or breaks a bond or does actual chemistry, then yes, you have to give it a name because something did happen there that was fundamentally a chemistry thing. But when you just rotate around bonds, actually, a lot of times you don't even see that happening because there's enough energy at room temperature. So room temperature is about 298 Kelvin. That's a lot of kelvins. So there's usually enough energy at room temperature to provide molecules plenty of energy to rotate around bonds, and so you don't really see the rotation occurring. It goes so fast you can't even notice it. Where you, I guess, would see conformational isomers being more easy to spot would be if you take them into a lab and you put in an instrument where you can have a Dewar attached to the instrument, and that Dewar might have something like liquid nitrogen or liquid helium. So you cool the thing down to 100 degrees below zero. Then all of a sudden the rotation starts to slow down, and maybe you get it to go slow enough so you can see the different rotamers or conformations around this. So when we look at conformational analysis, the best way to look at molecules is with a Newman projection. The Newman projection is where you take a molecule, it could be any molecule, and you sight down 2 of the carbons put one right behind the other one, eclipse them, and you sight down 2 of the carbons, and then everything else you draw as clock faces in the front and the back of those 2 carbons that you put together. The simplest one, which is ethane, we'll talk about, and I'll show you in another really short lecture coming up right after this. And then we'll look at something more complicated like butane, where there's more of an eclipsing interaction occurring that does not occur in ethane. So that's going to be the next video after that. So that's going to be the next 2 videos. So just remember, when you're thinking about what is a conformational isomer, swap out the word conformation with rotamer, so rotational isomer. And given that things can easily convert at room temperature through rotation on single bonds, that's sometimes a kind of a stretch to think of it as an actual isomer, but that's what the books define it as. Last topic. So when you're looking at rings, there's this thing called Baer angle string. Baer is named after Adolf von Baer, who was the person who came up with this concept and won the Nobel Prize for it. And this is the same Adolf Baer that was the head of the company Bayer Aspirin. Bayer became Bayer Pharmaceuticals, and so to this day we still have Bayer aspirin as an aspirin you can buy at Walgreens. So the same Adolf von Baer also did this work on looking at molecules and the ring strain associated with molecules. And you have to remember that the smaller rings get or the larger rings get, the more strain you get on the bonds, because the optimum geometry for 4 things bonded to a carbon. And if we're talking about carbons, we're talking about 4 things bonded to them, unless it's an alkene or an alkyne. But so for an alkane, we always look at carbon with 4 things bonded to it, and that means by definition it should always have 109.5 degree bond angles. But we know that in molecules there's going to be a change and push away from that. Sometimes that is going to be because of VSEPR. Sometimes it's going to be because of ring strain, and that's where the Baer angle strain comes in, because it was actually measured like how much energy is in that bond being strained versus how much energy is in the molecule itself, because it's got X number of atoms. This is all done with calorimetry. So you do calorimetry, you take these molecules, you burn them, and you say, okay, so if I take cyclobutane, and I know how much energy should be in the atoms of carbon and hydrogen in cyclobutane, which I can quickly ballpark estimate by looking at butane, right? So if I know that cyclobutane is supposed to have this amount of energy, and so I burn it in a polarimeter, and I get a whole lot more energy coming out, then I have to say, well, wait a minute, where in the world did all that extra energy come from? That's your angle strain. So you can actually get a quantitative number associated with your angle strain by looking at it in calorimetry and saying this excess number left over here, this really big, that has to come from the angle strain. One of the biggest ones coming from angle strain would be, of course, for cyclopropane, because if you try to make a cyclopropane with your model kit, then you will find that you might break some pieces trying to get that cyclopropane put together. That means there's a lot of angle strain in cyclopropane with a lot of energy that wants to be released. But once you understand and appreciate that, you can take advantage of that, because we can take cyclopropane rings or thulium rings in general, and we can use them as materials in syntheses because they're so strained they want to pop open. So we go ahead and let them pop open, and we'll let them pop open in these reactions where they will then react with other molecules that we want to, if we can direct that chemistry. So one of the things that we have as a sort of an outcome of the Bayer angle strain is a concept which has been around for a long time. How long? Well, so Adolf von Baer, Bayer Pharmaceuticals basically came into being between like World War I and World War II. And right around World War II, that was when it was at its highest power. And then after the war, it was broken up and chopped into pieces and given to countries around the world as sort of reparations for the war and what they had done with the Jews in the concentration camps. So, but anyway, and that's actually really interesting. If you're interested in history, if you're interested in chemistry, I highly recommend a book. It's called Aspirin, and it's the story of aspirin. It's the story of Bayer Pharmaceuticals, and it's the story of World War II, and the story of what happened with the concentration camps. And it's a fascinating story, and it's all about aspirin is the thing that holds the whole story together, which may sound kind of wonky and nerdy, but actually it's a really good book. It's a really good read. But anyway, so Adolf von Baer back in World War II, so he has this concept of this ring strain, and what he basically comes up with is a rule where the rule, and it's been around since World War II, and that rule is that, okay, so since we know that alkenes are sp2 hybridized, and if they're sp2 hybridized, they want to have 120-degree bond angles, then we know if I put an alkene in a bicyclic compound, like the one on the left here on the screen, which is a 2,2,1 bicyclo, that if I try to put that alkene right there on the bridgehead carbon, where I know that by definition this bond angle is supposed to be 120. I mean, look at it here. It almost looks like 90 here. And then here it's getting to the point where you're saying, okay, wait a minute, that's just way too much strain. So the rule has always been, and this is called Brett's rule, the rule has always been that small bicyclic compounds with double bonds at a bridgehead carbon should not be able to be made, because they should be highly, highly, highly unstable, highly strained. Now, you can do a double bond in a bicyclic if it's not on the bridgehead. So this one here, you would call this a 2,2,1 bicycloheptane. 2,2,1 bicycloheptene, and the alkene would be in the number 2 position. But to put it in the number 1 position, where it's at the bridgehead, according to Brett's rule says no, that's not possible. A few years back, I was reading through some literature, catching up on my organic chemistry reading, and I came across a paper. And the paper looked like this. And the thing that caught my eye was the title. Because as I'm reading through, I'm just flipping through the journal, and I see this title, it says the synthesis of an anti-Brett compound. I said, whoa, wait. Because actually, I'd been getting ready to just about teach that part of the course that fall in class. And so it's kind of timely that I found this article right before I started teaching this in class. And so I said, what do you mean anti-Brett? There's such a thing as an anti-Brett. And so I read the paper, and it turns out that not only did these people, so this is something that's common in chemistry. Whenever somebody has a rule, there are going to be chemists out there that are going to say, well, you know what, rules are made to be broken. So the hell with your rule, I'm going to figure out a way to get around it. And a lot of times a PhD project might be trying to figure out a way to break that rule. And when you break that rule, you're basically coming up with an experimental piece of data that doesn't, it's not explained by the rule. And so you can't change your experimental data. You have to change the rule itself. And so I don't know when this is going to show up in author textbooks. I'm kind of surprised, actually. It has not shown up yet. But what the textbooks in organic chemistry should say these days is no longer that Brett's rule says these compounds can't be made. What Brett's rule should say is that there's this Brett-ish type rule where, yes, they're highly strained, but that doesn't make them impossible. Because if you look at the molecule that these people made, so not only did they make an anti-Brett compound, they made a ridiculous anti-Brett compound. If you look at number 17 there, right? So they took a 3,2,2 bicyclo. So it's a bicyclo 3,2,2. Let's see, it's got 1, 2, 3, 4, 5, 6, 7, 8. That's a nonane or nonene or a nonadiene, right? So it's a 3,2,2. So excuse me, bicyclo 3,2,2. It's actually a nonatriene, right? There's 3 alkenes, a nonatriene. And when you put the numbering for those alkenes, one of those numberings is going to be right here at the bridgehead, and the other 2, I can buy the other 2. Those are I'm okay with. I mean, that's really, really strained. That's going to be really tough to make, but I can buy it. It can be made. Putting this one here on the bridgehead, I was always taught from the time I was your age that, nope, that's not going to happen. Well, they did do it, and they did it with not just this one alkene, but with 3 alkenes. And so those other 2 should make it even more unstable, because all those alkenes are sp2 hybridized, and they want to be 120-degree bond angles, right? So very strange compound, but they did make it. And that's something that, when people go to grad school, sometimes that's your PhD thesis is. It's just disproving somebody else, or filling out part of the work that they've done that they really couldn't figure out how to answer a certain question. Then you go ahead and answer that question for them with work you do, and a lot of times that's a really good way to get started in research and publications. Yes, there now are anti-Brett compounds in the world, and I think hopefully the organic chemistry will catch up pretty quick and say, let's no longer call this Brett's rule, let's call it maybe Brett's rule of thumb. Is maybe a better way to do it. Okay, so that's going to be our nomenclature for this chapter that we're doing.